Thank you very much for inviting me to present my work. My name is Andreas Nenning. I'm from the Technical Electrochemistry Research Division at TU Wien, which is led by Professor Jürgen Fleig. And I will talk about the reaction kinetics and defect chemistry of electrodes for solid oxide fuel cells and how they are linked to the surface chemistry and what I am planning to investigate in the future in collaboration with the TACO project. At first, I want to quickly introduce the research group of technical electrochemistry, which was founded in 2005 by Professor Jürgen Fleig. And the main topic of this research group is to understand the fundamentals of the kinetics and the defect chemistry of mixed conductors, especially in the use of solid oxide fuel cells, where oxygen redox reactions are important. Overall, we are mostly interested in the kinetics, which we can measure by electrochemical impedance spectroscopy of model solid oxide cells. And we combine this with different other analytic techniques to get a more complete picture of the defect and surface chemistry and how it relates to the electrochemical properties of the oxides. Recently, we also started to investigate all solid-state lithium batteries and photoelectrochemical cells. But today I will only talk about this SOFC-related topic. As a quick introduction, a solid oxide fuel cell is a high-temperature electrochemical device with an oxygen ion-conducting solid electrolyte. And this requires a relatively high temperature for sufficient oxygen ion conductivity. So we investigate our samples at 600 to 800 degrees. And the most important reactions that we investigate are the oxygen reduction reaction in oxygen atmosphere and the hydrogen oxidation or water splitting reaction at the anode side of the solid oxide fuel cells. Now, since for these reactions, when they are done electrochemically, we need oxygen vacancies or ionic carriers and electronic charge carriers. We need both of those available at the surface, and therefore mixed ion and electron conductors are the most promising materials candidates for fastest electrode kinetics. And I dedicate my research mostly on this class of materials. However, there are some challenges, especially regarding the stability, the degradation rate of the electrodes, as well as the variability of nominally equally prepared electrodes and model cells due to small changes in the PLD parameters during the electrode preparation or impurities or segregation effects. And yeah, I mainly want to tackle these segregation effects. Overall, we can fabricate several model electrode designs and model cell designs. However, one relatively simple design proved to be very useful if we are mostly interested in the kinetics of the surface reaction of the mixed conducting electrode. And this design is sketched here. The main part is mixed conducting thin film, of which we investigate the kinetic properties. And this film is deposited on a single crystalline YC oxygen ion conducting electrolyte. And since we want to use this as an electrode, we usually need to supplement an additional current collector, which is a photolithography defined platinum grid. And this gives us the electronic conductivity of the film. And furthermore, we need a counter electrode because we want to use this in an electrochemical cell. And therefore, we have a recipe for a porous GDC-based electrode, which has very fast kinetics and is stable in oxidizing and reducing atmosphere. And with such a cell, we can then measure the oxygen exchange activity and get information on the defect chemistry by electrochemical impedance spectroscopy. Overall, we are very interested in the defect chemistry of these materials because this is a very decisive, actually the decisive property for the electrochemical functionality of the materials. And one very often used prototype material is lanthanum strontium ferrite, or LSF, which is an acceptor-doped perovskite material. acceptor doping means that we have strontium 2+ on a lanthanum 3+ side. So we have a charge imbalance in the cation lattice. And this is compensated either by oxygen vacancies or by electronic defects, electron holes in oxidizing conditions. And the question whether the material forms oxygen vacancies or electron holes depends on temperature and oxygen partial pressure. And for LSF, this is already quite well understood. And it's shown here in the so-called Brouwer diagram, where the point defect concentrations are plotted versus oxygen partial pressure in a double logarithmic scale. And what you can see is that the LSF is a P-type hole conductor in oxidizing conditions with a comparatively small amount of oxygen vacancies in oxidizing conditions. And when we reduce the material, the electron hole concentration decreases and the charge compensation of the acceptor doping switches to primarily oxygen vacancy compensation. So the material becomes a better oxygen anion conductor in reducing conditions, and the electronic conduction mechanism switches from P-type to N-type. So we can tune the electrochemical properties of the bulk a lot by the oxygen partial pressure. And furthermore, when we go to very reducing conditions like dry hydrogen, metallic iron particles appear on the surface of the LSF, which we can see here in such a SEM picture of the surface. And they were also already observed by thermogravimetric measurements, where a constant mass loss at a certain very low partial pressure indicates the onset of decomposition. Now, why are we so interested in the defect chemistry of the materials when we actually want to investigate the oxygen exchange kinetics? And the reason for this lies in the nature of the electrochemical oxygen exchange reactions at solid-gas interfaces. Normally in electrochemistry, you would think you have some potential in your different phases, and when you switch on a cell voltage, you change these potentials, you get a potential step. And in most liquid electrochemical devices, the highest potential step is actually where your rate limiting process is located. However, in SOFCs, the rate limiting process is at the solid gas interface. And since the gas phase is an insulator, there is no defined potential step at the solid gas interface. So on first sight, it's actually a bit puzzling what is actually driving the electrochemical reaction. However, due to the electrochemical nature of the reaction, when we apply a cell voltage, also the effective oxygen partial pressure that defines the defect chemistry of the mixed conductor changes due to the applied voltage according to Nernst's equation, which is shown here. And as I have shown previously, the defect chemistry, so the concentration of oxygen vacancies and electronic carriers, depends on the oxygen partial pressure. So we alter the defect chemistry of the material, and thereby we trigger either the oxygen incorporation, oxygen release, as well as hydrogen oxidation or water splitting reaction, depending on the gas phase. And as long as we look at the bulk defect chemistry, this is mostly settled. However, surface defect chemistry and surface structure and surface composition, they differ vastly from the bulk. And this is actually the very tricky part to understand how the surface properties are related to the oxygen exchange properties. I just want to give you a quick introduction into our most important characterization method, which is impedance spectroscopy. Thereby, we apply a very small AC signal to the electrochemical cell, only 10 millivolts. In this regime, current and voltage are proportional, and we can measure a polarization resistance, which is a measure for the oxygen exchange reaction activity. And furthermore, due to the mixed conducting nature of the oxides that we investigate, the voltage also changes the oxygen stoichiometry. And also the altering of the oxygen stoichiometry gives a current as long as an AC signal is applied, and we can model this with a capacitor, which we call the chemical capacitance, which is a fingerprint property for the defect chemical state of the oxide. And then we can fit our data in many cases with such a relatively simple equivalent circuit, which consists of an electrolyte resistance, which is of ohmic nature, the polarization resistance as a measure for the oxygen exchange activity, and the chemical capacitance as a fingerprint for the defect chemical state. And then we get some semicircular curves in the complex impedance plane from which we interpret our electrochemical results. Furthermore, electrochemical impedance spectroscopy is a quite simple technique. It only requires 2 electrical measurement wires, in some cases also 3 or 4, attached to the sample. So it can be easily combined with other experimental techniques as long as we can fit wiring onto our sample in the experimental chamber. And one very powerful tool to further investigate the surface properties, which are decisive for the kinetics, is ambient pressure XPS combined with solid-state electrochemistry. And we are very happy that at the labs of Christoph Ramechan now there is an in-house ambient pressure XPS analyzer, and we can use this and have a very fruitful collaboration there. You can see a sketch of one of our model cells, which is this tiny black rectangle mounted in the ambient pressure XPS chamber and contacted. And here, this is the nozzle of the analyzer, which is brought very close to the sample so that the photoelectron path in the gas phase is short, and we can measure in 1 or 2 millibars of atmosphere and at the same time heat the sample and electrically polarize and characterize it. And as a first example, I want to show you some results on the strontium segregation on lanthanum strontium cobaltite electrodes, which is a known degradation source. And when we just anneal our lanthanum strontium cobaltite films in 1 millibar of oxygen to a high temperature, we can already see that the surface changes a lot from the SEM images here. So the roughness increases, and we get quite large particles that evolve on the surface, which are strontium rich. And from the simultaneously acquired XPS spectra, we can see that 3 different strontium and oxygen species are present on the surface. We have a bulk oxygen species, the blue species, which is most likely a strontium oxide, and a surface species, which is most likely strontium sulfate. And we can monitor then, as a function of temperature, how these species evolve with temperature and time, and also monitor the electrochemical polarization resistance at the same time. And what we can see here from this experiment is that the bulk strontium component, it decreases, which means it gets overgrown by primarily by the strontium oxide species. And this process already starts at 450 degrees, which is relatively low, given that in bulk diffusion experiments, you would expect that cations stay on their lattice side at this temperature. At higher temperature, the degradation rate slows down, most probably because the surface is reaching an equilibrium state. And also, these strontium-rich large particles are most likely not the main degradation source because they do not cover the entire surface area. They just do not look so nice. Another experiment on the degradation of the electrode is the comparison of the polarization resistance directly in the PLD chamber in which we deposit our thin film electrodes compared to the XC2 setups that we usually use normally, where we flush our setup with synthetic oxygen-nitrogen mixtures. And the interesting result, when we measure the kinetics of our cells directly after preparation within the PLD chamber, is that we get very low polarization resistance values, lower than what almost all the research groups around the world report. And this is relatively stable and reproducible. And once we just take it out of the chamber and put it into an XC2 setup, we get a 5 to 10 times increase in the polarization resistance. And very recently, in collaboration with Christoph Ramechan, we could find out that trace amounts of sulfur are the actual reason for this degradation. So for almost magical reason, in our PLD chamber, no sulfur traces seem to be present in the atmosphere. So we have very high kinetics, and when we investigate the pristine sample, we find no sulfur at all. And once we heat the sample in even very, very low partial pressures of oxygen, so 10 to minus 3 millibar is sufficient to get a significant amount of sulfur, which increases with annealing time, and also the degradation rate of the electrode is very fast. However, not all cation segregation phenomena are bad. There are also positive segregation phenomena, especially in reducing conditions, where metallic iron particles appear on the surface. And this metallic iron is anchored into the oxide. So you can see here that this is the oxide, and the particle is inside the oxide due to this segregation and exsolution process. And this makes it morphologically much more stable compared to an impregnated nanoparticle. And depending on temperature and strain and so on, we can really tune the size and number density of these particles and can achieve extremely high coverages, as shown by Wang et al. In a recent publication. And from electrochemistry, we can see that these metal iron particles are really catalyzing the water splitting reaction. And this is the reason why, in presence of metallic iron, the water splitting branch of the current voltage curve, cathodic polarization, is much faster than the anodic hydrogen oxidation reaction. And we believe that the adsorption and dissociation of the hydrogen is the rate limiting step on the pure oxide. And this process is much faster on the metal particle. And then the adsorbed and dissociated hydrogen can diffuse on the oxide surface. Furthermore, we can measure the degree of reduction of the oxide in the XPS chamber. But I will skip this due to time. And by XRD data, we could show that the iron particles, once exsolved, remain on the surface, and they are just transformed into iron oxides, but they do not diffuse back into the perovskite oxide. So the reverse of the iron exsolution process is much slower kinetically compared to the exsolution itself. So to sum up, we have found that in higher oxygen partial pressures, strontium and azide-rich precipitates form on the surface, and this leads to azide deficiency in the perovskite lattice. In reducing conditions, metal ions, especially iron and other reducible transmission metals, precipitate to the surface, and this leads to B-side deficiency. So actually, the thermodynamically stable A to B stoichiometry of the perovskite depends on the oxygen partial pressure, and the surface terminations depend also on the cation defect chemistry of the perovskite. And there should be some thermodynamically stable A to B stoichiometry for each material, partial pressure, and temperature. And we want to explore this more in the future. So a quick glance on the Planst experiments. Due to this always observed segregation phenomena and the need to have stable, highly active surfaces of perovskites for catalytic and SOFC applications, we want to investigate the effect of A to B non-stoichiometry on the surface stability of LSF in various oxidizing and reducing conditions. And we will do this first by thermogravimetric analysis and chemical capacitance measurements, which is giving us information on the bulk defect chemistry. Furthermore, we want to collaborate with the Ramechan group to get more information on the surface chemistry, because this changes a lot when you have the segregation phenomena. And the overall goal is to achieve stable and reactive surfaces, and in the most ideal case, even atomically understood reconstructions of the surface, which is, of course, a very, very demanding task, but maybe we are successful. And a recent result from collaboration of Riva and Kubitschek from our group has shown that on atomically resolved strontium titanate single crystals with two different orientations, the oxygen exchange reaction kinetics differ due to the surface atomic structure. So we have shown that this is possible for the, let's say, more simple case of strontium titanate, for which the Diebold group already did a lot of work on the reconstruction of the atomic surface structure. Furthermore, we want to investigate why the exsolution and cation segregation processes are so fast. Because actually, from bulk diffusion experiments that were carried out in ambient air on thin film multilayers of perovskite thin films, A and B side cation diffusion coefficients were determined by Kubitschek. And what he found is that at relatively low temperatures, below 600 degrees, the diffusion coefficient is very slow. And actually, all cations should remain on their lattice sides. However, in reducing conditions where metal iron particles appear on the LSF surface, 10 nanometer size particles are formed at 400 degrees. And those are roughly 10,000 times larger than what we actually expect from the iron diffusion coefficient. And well, we have some ideas why this is the case. It's most likely due to an altered oxygen and also cation defect chemistry in the reducing conditions, and especially during exsolution conditions where a much higher amount of A and B sides and oxygen vacancies are present in the material, which ease the motion of the cations. And we want to investigate this by extending these cation tracer diffusion experiments at various partial pressures, and especially also at conditions where metal iron exhausts from the LSF. Okay, so a quick conclusion on my talk. Model solid oxide cells are a very good design to investigate the kinetics and defect chemistry of our mixed conducting catalysts. However, the surface chemistry, in which we are mostly interested, is very different from the bulk, but still at the high temperature, it will equilibrate over some time scale with the bulk defect chemistry. So we need to understand the bulk defect chemistry in order to know at which conditions the surface chemistry is at least stable. Also, we have shown that metal segregations can catalyze reactions, especially water splitting, whereas strontium segregation as well as impurities can really hamper the kinetics. And we have shown that the cation segregation depends very much on the oxygen partial pressure and the A to B stoichiometry in the perovskite as well as the temperature. And we need to understand this more to achieve more stable perovskite surfaces and get more information on the actual atomic reaction mechanisms. So thank you for your attention, and there is some time for questions, and I am happy to answer them.
Thank you very much. Are there questions? I was wondering about the sulfur. Do you have an idea? If it's 10 to the minus 3 oxygen, it shouldn't still come from the gas phase. So is it just diffusing out? Maybe the oxygen drags it out, so to say, and is it a small bulk impurity, or?
Actually, we still believe that it is part of the gas phase for some reasons. Firstly, we have measured the sulfur content in the bottled gases, and this is in the order of some 100 parts per billion.
Okay.
And interestingly, in our PLD chamber, somehow these amorphous oxide residues that, and the dirt on the chamber walls is probably a very active getter material for these sulfur species, because when we measure the outlet gas of the PLD, we do not detect the sulfur anymore. And furthermore, in the PLD chamber, when we heat our samples, in the same oxygen partial pressure, we have no sulfur on the surface afterwards. So it's unlikely that it's coming from the bulk.
So how do you measure the sulfur? Because mass spectroscopy is just on the mass 32, is it?
Yes. No, not by mass spec. It was, I think, by optical emission spectroscopy.
Okay.
So it was a small liquid trap which was condensing all the sulfur for a while, and then we went to Andreas Limbeck's lab where we did ICP measurements.
Interesting to know, yeah.
So we use usually the 5.0 oxygen and nitrogen. Maybe the 6. I think the 6.0 is more clean.
From the big cylinders or the small
big cylinders?
Okay. Questions? Michele.
Hi, thanks for the nice talk. I was wondering about the cation segregation that you see, especially at reducing conditions or oxidizing conditions. How much, so these films, are they single crystalline, or are they, do they have grain boundaries? Because it may also be that these cations preferentially diffuse along grain boundaries, and that's why you can.
So we investigated both epitaxial and polycrystalline films. And we see quite significant cation segregation on both films. On the polycrystalline films, which we deposit directly on the YSC, it's usually more pronounced, but it's definitely very significant also on the single crystallines. So, for example, the films with the highest number density of particles shown here, which were exhausted at only 400 degrees. These were epitaxial on perovskite substrates with different strain state.
I mean, one thing that came also into my mind, in principle, you can circumvent the bulk diffusion by just having lot of mobility of steps at the surface, because surface diffusion is many orders of magnitude faster than bulk diffusion. But then probably you, I don't know, did you do AFM and maybe have a look whether you see sometimes you get voids from this or things like that in the surface, depressions?
So I think the surface roughness does not increase that dramatically during the exsolution process. And I think there are even reports that where exsolutions are happening and even step terraces are still visible on the rest of the oxide. So it seems to be a very localized phenomenon where defects accumulate and an exsolution appears. Of course, in the exsolution, there must be a lot of cation motion, and also the bulk deforms because it's forming a void in which the particle is anchored. But this appears to be very located to the exhaust particle.
So you'll see something like this going down, then the particle, and then so the particle is sitting somehow in a ditch or in a depression, or you see that, or if you say there's a void, yeah.
So with the very small particles, it's hard to observe. But so the model is that first a well is forming, and then the particle is dissolving into the well, and once the particle sits there, it's basically just filling the well. But I have to admit that this depends very much on the material and exsolution conditions, because you have very many parameters to tune. So it's there is probably not one single simple answer in all cases.
Okay. If there are no more questions, then let's thank the speaker again.